General Physics 1. And now, here's your professor, Varanga Pereira.
Hello everyone, welcome back. So we started talking about fluids last time, so we'll continue talking about that today as well, ending that segment of this set of topics on fluids. Last time we talked about fluid statics, right? When you have a fluid at rest, if you let your water bottle come to a rest, and then you can see the pressure as a function of time. We can talk about buoyancy, things like that. Now today, switching to the computer here, we're going to start thinking about fluids in motion or fluid dynamics, right? So in the case of the human body, where you have blood flowing through, that's a case where certainly your blood is not just staying put, right? So it's moving around your body. How do you deal with those sorts of situations? A little bit more complicated of a topic. Really, you should take a class on fluids to properly go through, especially fluid dynamics. It requires kind of in-depth analysis to really appreciate what it is. We'll try to get a rough overview of what fluid dynamics is today so that you can kind of understand things like how airplanes work and things that are really important, right? So where fluid motion is really critical. So there's a picture of the Wright brothers plane. The first, essentially the modern airplane comes from this, right? It's not the first to fly, but it's the first one that was powered and controlled and sustained, and there's a human in it, right? So there's, in a lot of ways, the first airplane, if you kind of think of it in the modern sense. If you're in Washington, D.C., you can go see the real thing. So this is a picture of the real thing. It's not a replica, it's the real thing that was flown by the Wright brothers, right? So in 1903. Airplanes, like I said, requires fluid motion, right? So here's animation that shows you a cutout of an airplane wing. So this kind of eye drop shaped thing in the middle, that's a cutout of an airplane's wing, and you kind of notice that it's kind of bulging out in the front and it's kind of tapered towards the back. Probably familiar if you've flown an airplane, looked out the window. This is kind of the shape of a wing, and they put certain dyes to make the air visible, essentially. That's why you're seeing these lines. And so if I hit play, notice what you're observing, right? So the air is flowing from left going right. Notice it's very smooth at the very beginning, right? It goes over the wing, under the wing, and once it comes out the back, you can see it's kind of shaking a lot more, right? It's not as smooth, right? So something just to notice. This motion is what creates lift, right? So that's why airplanes are able to fly, is that the air is going over and under, and that effect creates lift, right? So here's kind of a slow motion just to see how the different segments of the air goes above and below the wing, right? Fundamentally, this requires viscosity, right? The stickiness, which we'll talk about, right? It's not density, right? So density is mass per unit volume. Viscosity is a different property, right? So think about pouring syrup onto your pancakes versus water. You shouldn't be pouring water, but you get the idea, right? So if you pour water, if you pour syrup, oil, they'll pour differently, and that's a different kind of set of considerations to the density, mass per unit volume. Two fluids could have the same density, but they could have different viscosities. The higher the viscosity is, the more syrupy it is, right? So more viscous it is, right? So for airplanes to work, you need viscosity. It wouldn't work without viscosity. So you need a little bit of stickiness to the air, right? So let's talk all about these new terms that we need to consider. So when we talk about fluids in motion, we're really talking about two different regimes, laminar and turbulent. Laminar is what you saw at the very beginning of that airplane's wing, where it's really smooth, right? That there's no turbulence, right? Just like the word implies. And so we'll compare those two flows. We'll talk about the continuity equation, right? It's really a statement of conservation of mass, that if you have a certain amount of mass coming in, that same amount of mass should be going out, right? So think about a pipe water's flowing in, water's flowing out, the same mass that flowed in must flow out, right? You can't just have mass just disappearing somewhere, right? We'll talk about the Bernoulli equation carefully as much as we can. This is a very popular equation that is often misused and misunderstood, right? So it's a very interesting equation. It's a statement of the conservation of energy, which we'll talk about starting next class. So it's a nice statement of the conservation of energy, but we have to be really careful when it applies. It applies to very specific situations, and if you try to apply it to situations where the constraints are not met, then you're not going to get an answer that's very accurate. At the end, we'll talk about viscosity, right? What that entails. Like I said, the rough idea of viscosity is that it's kind of the stickiness of a fluid. At the end of the class, we can talk about midterm 2. So if you have questions about that, put it on add discussion under today's thread, right? I guess you could put it on the midterm 2 thread, but it'll make it easier for us to keep track of the questions if you just put it on class 14's general thread, so that Jericho's here, he can kind of compile those questions and we can talk about it at the end, right? So if you have questions about the homeworks 3 and 4, you just have general questions about the concepts we've covered. You want to talk about friction, let us know, we can kind of go over it again, right? Okay, going through the difference between laminar and turbulent flow. Next time, let's say you're boiling some water, right? You have a candle that's lit in your room. Notice this pattern, right? So notice at the bottom of this video, the flow is very smooth at times. Notice that, right? Right into this moment is very smooth. And then towards the top, you see the swirling and twisting around, right? So that's the difference, right? So laminar flow, very smooth, right? Kind of very orderly. It goes from one place to another, kind of well behaved. Turbulent flow is very chaotic, right? It's really hard to predict exactly what the behavior is, right? So it's twisting and turning, and you generally get both kinds of flow, whether it be an airplane wing or you're talking about a fluid going through a pipe, let's say water coming to your house, for instance, right? So you generally have both of these flows to consider, right? So just generally, that's what it is. Next time you have a lit candle or something like that, notice how kind of the smoke is going above, right? So some of that is very smooth, laminar flow, and some of it is twisting and turning like this, right? Okay, let's go to our notes and start thinking about fluid dynamics. Okay, so usually when we talk about fluid dynamics, to keep things simple, what we do oftentimes is to ignore viscosity. Okay, viscosity is really important. Airplanes don't work without viscosity, right? So just ignoring that, you might seem like, oh, this is a bad idea, right? Like I said, it's really important. However, think about it like friction, right? So think about how when we first started off talking about something moving, we ignored friction, we ignored air resistance, right? Because it makes it easier, simple to build a model that is roughly correct, and then we can improve it, right? So viscosity we can add later so that we don't kind of make it too complicated to start with, right? So we're going to highly simplify this to start and consider the two types of flow, right? So just kind of keep that in mind. We're going to leave aside viscosity for a lot of this discussion. We'll talk about viscosity later in the class. So the two types of flow we will encounter we said was laminar flow and turbulent flow. So think about water going through a pipe. Okay? So in the case of laminar flow, what you could observe is that the water is very smooth, right? So the water that starts right here smoothly goes over here, right? The water that's over here doesn't mix and kind of tumble along and end up here, right? So the water here smoothly gets across here. The water here smoothly gets across here, right? So laminar flow is like that. So watch your candle if you have it, right? Or if you're making pasta or something, watch the steam rising from the pot. You'll see that towards the source, right, where it's rising from, you'll get this sort of very smooth behavior. On the other side, to contrast this, if you think about turbulent flow, what does that look like? Well, as you saw, it's tumbling, it's twisting and turning, right? It's rather chaotic motion, right? So the water that's here doesn't kind of smoothly get across here. The water that's here might end up kind of over here as it goes through this pipe, right? So it twists and turns and it's tumbling around and it's a bit chaotic, right? So those are the two that you will encounter. This is a lot harder to analyze. Oftentimes you use computers to kind of try to understand how turbulent flow behaves because you're not going to get a simple equation to model this, right? Laminar flow, still fairly complicated, but you can actually do a little bit of math to describe this. Because it's so smooth and because it's so well behaved, there are equations that you can use to describe laminar flow rather simply, right? But if you're really talking about turbulent flow, you really have to model it using a computer because the equations are really, really hard to solve on paper, right, for this sort of thing. Okay, so let's talk about flowing across a tube, right? So one of the things that you may want to know if you're talking about blood flow through your body, if you're talking about an IV that you're connecting to a patient, for instance, you want to know flow rate, right? How much of a fluid is it getting across, right? And we're going to say that flow rate, we're going to say is Q, and that's described as the derivative of volume with respect to time, right? So be careful, V here is not velocity, right? This is volume. And remember that you can get a volume as long as you have an area and you multiply by some length, right? So this cross section could be your area, and then you have a certain length, right, for your tube. And if you multiply length by area, you will get volume, right? So what this is saying is if you focus on, let's say, a small segment of your pipe, how much volume is going through it per unit time, right? So let's try to reorganize this a little bit by using the terms area and length. So if I have a derivative with respect to time, volume I'm going to rewrite as area times the length. I'll call it x because I'm going to do a derivative, and the length I'm going to call x, right? So the area of this pipe may not change, right? Maybe it's a constant area. So if I pull that out of the derivative, I'm left with dx dt, which is velocity, right? Length over time, right? So a derivative of position or over time, right? So that's velocity. So what we're left with is that the flow rate is the area times velocity now, right? So too many V's. Sorry, that's how it goes. But yeah, the big V I'm using as volume, the little v I'm using as velocity. Okay, this is velocity. So a different way to say the same thing, that if you were talking about the flow rate, you're talking about how much volume is going through per unit time, and you can calculate that as long as you know the cross-sectional area of what you're considering, let's say a tube, if you're talking about a vein, right, what's the cross-sectional area of it? And if you multiply by the velocity of the fluid, you can get a flow rate, right? So just another way to say the same kind of concept. So either you think of it as volume per time, or you think of it as area times velocity. Okay, so let's think about a situation where the pipe changes shape, right? So if you look at the veins in your hand or your body, right, it's not a single pipe that gets across all the blood across your body, right? They change shape. So what if you have a situation where your pipe changes shape, right? What happens then, right? So if you have something like that, where you have a larger area becoming a smaller area, right? So all that's flowing through, what happens to it, right? So we're going to assume this is simplified. So there's certain assumptions here, right? So one of which is we're still ignoring viscosity. We'll assume that the flow flows smoothly, right? So it goes like this. It smoothly goes across like this. Right? And you probably know this from experience, right? So that if you have situations like this, maybe it's your garden hose or something that you're pinching, right? So you've probably seen situations like this where there's flow through one size of a pipe and then it's a smaller one, or vice versa, that you're going from a small one to a large one, right? So you probably encountered stuff like this. So this is getting at the continuity equation. Okay, because we have to think about, okay, what stays the same, right? So clearly something's changing when you try to send fluid in this space to this space. Something should change, but something should stay the same, right? And what the continuity equation is really saying is it's, AKA, this is just the conservation of mass, right? Maybe you've seen it in chemistry, right? Conservation of mass, you can't create or destroy mass is the idea. So if you have water going through a certain pipe that has a certain size and it gets squeezed into it, then the amount of water shouldn't just change, right? You can't have water just disappearing or appearing inside of the pipe all of a sudden, right? So what goes in must come out, essentially, is what it's saying. So knowing that we have this idea of a flow rate, what can we do with that? So the continuity equation will say that the flow rate here in this first segment should equal the flow rate in the second segment. Okay? Think about why, right? We're saying there's a certain amount of volume per time that's going through, right, in this area, a certain volume of water, and we're saying that same volume must come out of the other side, right? And one of the assumptions that's made here is that the fluid that you're considering is incompressible, right? You can't squeeze it and change its shape, essentially, right? So not a great assumption for air. Air is fairly compressible in a lot of cases. But a very good assumption, right? It's pretty decent for water. Water, right? Try to put water in a container and try to squeeze the water. It's not easy to do, right? If you try to do that, fill it up with some deformable container and try to physically change the volume of the water. Try to take a certain amount of water, right, as a certain volume, and try to squeeze it into something smaller. You know you can do this with air, right? If you put air into a balloon and you squeeze the balloon, you can change the volume of the air fairly easily, right? You can use your hands to change that. So air is fairly compressible. water, incompressible. A lot of fluids are actually behave in an incompressible way, right? A lot of times. So there's an assumption there, right? So you're not going to be able to change the volume. So if this much volume of water is going in, that much volume of water has to come out the other side. So we can use our relationship that area and velocity are related like this, right? With the flow rate, and we can say that area 1 times the volume. Sorry, yeah, I got to be careful too. The velocity 1 is equal to area 2 velocity 2. Okay, so this gives you kind of the idea, maybe if you've seen from playing around with your garden hose, that if you have a garden hose and you squeeze, right, one end of it, you'll probably notice that the flow gets faster, right? And that's what you're seeing here, right? Because if area 1 is larger than area 2, right, for this to be equal, then velocity 2 must be larger than velocity 1. Right? Does that make sense? Right? So that's where that comes from. If you try to squeeze, right, there's some flow and you try to squeeze it, and you'll get that speeding up of the flow, and that's because, well, you still have to maintain this, you still have to send the same amount of volume per unit time across, and to do that, right, because you have less areas to work with, you have to go faster. Right? So that's where that comes in, the garden hose kind of effect. If you have not done it, you can go ahead, take a tube, you can take a straw, right, send water through the straw, pinch one side, and you'll notice that out the pinch side, water's going faster, right? Now, you can generalize this idea. Now, this, of course, this relationship works, right, for incompressible flow, okay? But like I said, doesn't really work really well for air, but maybe you want to deal with air, right? Maybe that's what you want to consider. You can generalize this, and the way you generalize this is not to start with the flow rate, not to think about volume per time, but to go all the way to the beginning, all the way to the more fundamental idea of conservation of mass, and saying, well, I know for a fact that if I send a certain amount of mass through this, that certain amount of mass better come out the other side, right? Compressible or not, right? So that's the way you kind of generalize it, is to start before that, before this point, you can say, actually, what must be true is the mass rate, right? Mass per unit time, the dot is saying mass dm dt, right, is what I'm saying is m dot, right? You might have seen that from calculus. M dot, mass flow rate, right, at one section must equal the mass flow through the other section, right? This is a more general idea than the flow rate, right? The flow rate's arguing about volumes, saying the volume must be the same. Mass is more fundamental, right? Because you can't create or destroy mass there. So we're saying, okay, well, let's go to a more fundamental idea, and that way we can relax this constraint and say we can deal with any flow, compressible or incompressible, right? And when you do that, writing this in terms of a mass flow rate, the way you do that is to say, oh, I just have to multiply by density. So each side, if you multiply by density, rho 1, area 1, velocity 1 is equal to rho 2, area 2, velocity 2. Now you have the continuity equation that'll work for any flow, right? So compressible or incompressible. Notice that in the case where density 1 and density 2 are the same, right? Incompressible, you can't change the volume and therefore change the density of the fluid. If rho 1 and rho 2 are the same, they cancel and become this, right? So this is the more general idea, is that, oh, if you do have compressible flow, that when it's in one section it has a certain density, and when it's in the other section it has a different density, this will do it, right? This will work. And if you check the units, it works out, right? Because the units of area times velocity is volume per time. Check the units, right? It'll work out. If you check the units of this, right? Density is kilograms per meter cubed, right? Mass per volume. And if you check the units of this, what you're going to have is kilograms per second, right? So kilograms per second on both sides. So if you do the checking of units on this side, checking of the units on this side, they're both going to give you kilograms per second, which is the mass flow rate. Right? Generally, so this works for incompressible or compressible, this only for incompressible flow, right? How are we doing in terms of questions?
Everything seems good.
Okay, so far, okay, doing okay? If you have a question, throw it into a discussion. I know it takes a second to type the questions, so I'll pause from time to time.
We have someone asked what the little dot over the M was again.
Oh yeah, so it's just a symbol that means mass. If we go to the notes here, m dot means mass per time. Okay, so the dot just means it's a shorter way of writing. So you can also rewrite this if you like. Instead of writing it this way, you can write the same thing as dm dt 1 is equal to dm dt 2. Right? This is a little bit messier of a way to write, so that's why this is written this way. This is essentially saying the derivative of mass with respect to time, one section versus the other, right? So like the dot notation you may have seen in your calculus class, sometimes you use a prime notation, right? So there are different ways to say derivative.
A follow-up to that was, how is there a change of mass if it's conserved?
Oh, right, good question. So it's a mass that's going through a particular section per time, right? Let's say this is our section 1, right? And of course I'm drawing this on paper, right? But just kind of try to use your imagination and think about water flowing through this pipe, right? So if I look at this section, this is my section 1, in 1 second, how much mass went through this thing, right? Or let's say in 1 hour, how much mass went through this, right? This section. That's what we're saying is m dot, right? Yes, mass is conserved, right? So the mass that exists. But the thing with fluid motion is that, yes, there's a certain amount of mass, but it's moving through some space, right? So that change is what we're talking about. Not the fact that mass is created or destroyed, but mass going through a certain section of the tube, right? Does that make sense, hopefully? All right, let's try an Instapoll. Keep asking questions. And take a look at this Instapoll and we can carry on from there. Okay, so here's the scenario. We have our options shown up on your device, right? So take a look at this. I'm going to zoom into the question here. We'll take a minute and a half. Take a look, ask questions on that discussion. We'll be back in a bit. Let's see. Okay, answers are coming in. We'll give you a couple of seconds more to put in your answer. Okay, so let's start looking at the results. Okay, the one with the radius of 3 millimeters, right? So the smaller one, what's the speed at which the liquid is going the highest, right? So switching to our notes, we know from our continuity equation, right? So we can think of the soda as incompressible, right? Just kind of as an assumption, we can do that. We only know the areas, and we're asked to find how the velocities change, right? So if you have some flow through a larger straw pipe, and you send it through a smaller one, right? If the area of the second part is smaller, the velocity must be higher, right? Reverse is also true. If you send it through the small one and it ends up in the large one, then when you go through the large one, the velocity will slow down, right? So try this out with a straw, garden hose, any kind of somewhat of a pipe that you have. You can send liquid through it and then see this effect, right? So that has to do with the continuity equation, has to do with mass conservation. All right, let's use this to do a problem and something akin to something you see in the real world, right? So let's say we have a hose. Okay, we have a hose, and there's a certain nozzle that you connect to the hose. Okay, there's a nozzle, and you have water coming through, right, through that, and then off to fall into a bucket. Okay, maybe doing some gardening, and you're trying to see if you can fill this bucket with water. So here's the water flowing down, right, from the pipe. And we know that the volume of this container, this bucket, is 30 liters. And you time this and you realize, okay, you can fill this in 1 minute. Okay, so you can fill this bucket 30 liters in 1 minute. You have a certain diameter to this. The diameter at the beginning is 2.5 centimeters, and we're given an area here of the nozzle, 0.5 centimeters squared. Okay. What we need to do is figure out how fast is the water coming out at this point. Okay. At the point of the nozzle, how fast is the water coming out for all of this to work out, right? We don't know that information. We want to try to solve it, right? So take a moment to think about how you might do this, right? And if you have ideas, throw it into a discussion about how you might approach this. Okay, so let's think about how you would do this. You have to kind of think through this a little bit, right? So it's not just take one equation and apply it. You want to kind of think about a strategy here. You know certain things, or you know the information about the bucket, how big it is, how long it takes to fill it, and we're trying to figure out the information about the hose, right? Okay, do we have thoughts on how you would do this? How would you approach this? How would you figure out the velocity right there? What's this velocity? Let's describe what we know. What can we know about what's happening through the hose based on the bucket's information? Do we know something about this?
We have a response saying, I think you should be able to find velocity by setting the volume over time equals to the area times velocity.
Yeah, so good. So volume over time we know, right? So the water came from the hose. This 30 liters of water came from the hose, and it took a minute, right? So all this volume came from the hose, right? So that is a hint to think about flow rate, right? So water, incompressible fluid, we can treat it that way. So Q1 is equal to Q2 is the kind of the idea we want to be thinking about, right? So the total volume per time we know. So the flow rate kind of we know, right? And the issue here is that the hose is not just kind of constant diameter, it changes shape at the end, right? So we can treat the first part of the hose as 1 and the second part of the hose as 2, right? So we can say that area 1, velocity 1 is equal to area 2, velocity 2, right? So we can kind of start thinking about that, right? So let's say, can we determine how much came here, right? Q1, volume per time that came from this side, can we figure that out? Well, yeah, right? So because Q1 is equal to what? The change of volume, right? How much volume of fluid went through a certain change of time. But we know that, right? We know that's 30 liters per 60 seconds, right? That's our Q, right? That's our Q for both of them, but we're just kind of thinking about it for the first segment, Q1, right? That much volume went through in that much time. What's area 1? Let's try to figure out area 1. Area 1 is equal to, well, we're given a diameter. We can use that, right? So the area of a circle, right? The cross section of a hose is a circle. So the area of a circle is pi r squared, which is equal to pi. If we write it in terms of the diameter divided by 2 is the radius. Square that, right? We have pi diameter squared divided by 4. Now we can put in the numbers, right? So we have pi. The diameter is given as 2.5 centimeters squared, and then divide by 4 is equal to 4.91 centimeters squared. You'll see why I'm using centimeters in a second, right? It's intentional. Usually you should use meters, but here it's convenient to use centimeters because of the liters. You'll see in a second. Okay, so we have the area, right? So then we can say Q1, right, is 30 liters per 60 seconds. Okay, what is a liter, right? So just think about what a liter is. When we say 1 liter, what do we mean? We mean a cube that's 10 centimeters on each side, right? You can kind of, if you have a ruler in front of you, 10 centimeters by 10 centimeters by 10 centimeters, that cube is a liter, right? So we can convert this to centimeters cubed per second, right? So we can take our Q1 and say that is 30 times 10 centimeters cubed divided by 60 seconds will give us 500 cubic centimeters per second, right? This is why I was using centimeters for area, right? Because it's easier to just stick with centimeters when you're dealing with liters. Okay, so then now we can go ahead and say, okay, we can calculate the velocity 1. The velocity at the beginning of the hose is equal to Q1 divided by area 1. Well, that is 500 centimeters cubed per second divided by 4.91 centimeters squared, which is equal to 101.9 centimeters per second, right? And if you want it in meters per second, you can say 1.019 meters per second, okay? We're still not done because we just figured out the velocity through this part of the hose. We're asked to find velocity right at the end, right where it's dripping into the bucket. So we need to figure out what velocity 2 is, right? So velocity 2, using this relationship, right, our continuity equation, will tell us that volume 2 is, the velocity 2, I got to keep watching my phrasing because it's easy to say volume and I mean velocity. Catch me and correct me if I say the wrong thing. So velocity 2, velocity 1, area 1 divided by area 2. Okay, so we're just rewriting the continuity equation. Now we know all the values for this, 1.019 meters per second, and then 4.91 centimeters squared, 0.5 centimeters squared, right? We know area 2 because it's given here, and that'll give us 10 meters per second, right? That's the speed at which the water is flowing right at the end of the hose through that nozzle, right? So you can see, using things you know, right, things you've learned, now you can start doing some kind of practical examples, right, things that you might actually want to do at your house in your day-to-day life. You can start doing some calculations based on what you know. How are we doing in terms of questions?
No questions.
Okay, so doing okay?
Clarification question. We separated the hose, just to be clear, we separated the hose by saying the first part is area 1 and volume 1, or velocity 1, and the nozzle of the hose is V2 and A2.
Yes, right. Yeah, so we're dividing the hose kind of like this. It's almost the exact same situation. This part we're treating as the nozzle. This is the rest of the hose. So the hose comes in, the nozzle squeezes the flow, and that's exactly what we're doing here, right? So we're using the continuity equation mostly focused on the hose itself, mostly focused on this situation. We're using the information of the bucket because whatever went through the hose ended up on the bucket, right? So in terms of the Q, that could be related. The flow rate into the bucket right, is also the flow rate through the individual parts of the hose, right? So imagine if you extended this in a third segment, you can say Q1 is equal to Q2 is equal to Q3. Essentially, that's kind of what we're doing with the bucket, right? We're treating the bucket as a Q3, if you will.
Another question was, can't we just solve V2 by dividing Q by the area of the nozzle?
Can we not find V2 by, say that one more time, dividing?
The Q1, I'm assuming the Q1 by area 2.
Q1
So-
by area 2. Yes, yes. So Q1 we found here, right? And yes, area 2, right? If you should work, yeah. Because Q1 is this, right? So Q1 is equal to area 1 times velocity 1, right? So if we're trying to solve for velocity 2, if you take the area 2 divided by Q1, that should be the same, right?
Another question was, how did you get the V1 is equal to Q1 over A1?
V1 is equal to Q1. Okay, so this, yeah, so this is just rewriting the definition of what a flow rate is, right? So Q1 is equal to, right, so Q1 is equal to area 1, velocity 1. Right, and it's just rearranging the terms here to get velocity 1. Okay, keep the questions coming. We will now consider what happens if we make our pipe even more complicated, right? Because where we started was to say, okay, what happens if you just had a pipe and then that's it, right? It has a certain diameter, it has a certain area, it doesn't change, it's a constant area, constant diameter, constant radius, right? So just carries on, that's all it is. Then we're talking about a flow rate, right? So we can figure out how much volume is going through time. As long as we know area, we know the velocity, and that doesn't change, right? Because if this just goes on for a long, long while, the flow rate is the flow rate, no big deal, right? If you have a change in size, if you have this going into this, it gets smaller. Now you have to be a little bit careful. We'll still say the flow rate is the same. Q1 is equal to Q2, but what's changing is the velocity, right? If you change the area, the velocity will change. Something's got to change, right? Because if you're squeezing the flow through a smaller space, something's got to give, and that what gives is the velocity. The velocity gets faster. So what happens if we have more complexity, right? And what I mean is, what if our pipe not only changes shape, right? Well, let's say here's our pipe, but instead of changing shape only, what if it changes shape and changes elevation like this? Okay, now this could be your plumbing in your house. Maybe your house is on a hill or at the bottom of a valley or whatever it is, right? So the plumbing, right? So the pipes that bring the water in may need to change shape and rise above the mountain or the hill or some situation like that. This could be your blood flowing through your body, right? Your head is above the ground, right? So as your heart is pumping blood to your brain or your blood is flowing down to your legs, right? So not only are the shapes of the veins and the pipes themselves changing, but the pipe could actually change elevation too, right? So now it's a little bit more complicated a scenario. So let's see what we can do with that. We'll still say, okay, this is our segment 1, and over here is segment 2, right? The beginning of this and the end of that we'll call 1 and 2. And this is an application of Bernoulli's equation. So you need Bernoulli's equation to deal with more complex situations like this. You can deal with situations like this just with the continuity equation. That's all you need, right? You don't have to deal with changing elevation. All you have to do is, okay, does it change shape? You said just a geometric effect, right? So area, velocity, velocity, right? But if you have a situation like this where it's now more complicated, you have to bring in the Bernoulli equation, which is a conservation of energy. It's a more general idea, right? Still, we're going to consider the laminar flow. Very smooth, right? So I'm just going to draw just one line showing the water very smoothly going across this tube, right? It's not tumbling and turning. It's not doing any of that. Okay? And what we need is, because this is changing elevation, we need to establish where the ground is. And we need to measure the distance to various points. So one of the distances we're interested in is the very beginning of the flow. If we identify one of these lines, it's called a streamline. The term is not that important for our sake here, but one of the lines that the water is flowing through, right? So it could be this one, there's one up here. I'm not going to draw it and clutter up the diagram, but each kind of location of the pipe has a streamline, right? The water up here smoothly flows all the way here. Water here smoothly flows all the way there, right? Water here smoothly flows all the way to the top, right? They're streamlines, right? So a way to visualize those kinds of points of the flow. If you identify one streamline, you want to think about, okay, how high is it above the ground? Okay, and then you go over here at the very end of it and you just do the same thing. You say, okay, y2, how high is this point? Right? And this is a general thing, so if you have a different scenario where this falls down, instead the pipe actually goes down, fine. You can have a certain reference height and measure to it, right? The point is to, the reference itself doesn't matter, the point is to identify, hey, how different are these points in terms of height? Okay. So when you're applying Bernoulli's equation, let's be really careful and not abuse the equation, because a lot of times it's misused way too much. So let's be careful about when to use Bernoulli's equation. Certain things must be true. One is the flow should be incompressible. Okay? At least the one we're going to write down. There is a Bernoulli's equation that applies to compressible flow. There is a more complicated looking Bernoulli's equation that applies for compressible flow. But the one we're going to write down is for incompressible flow. Good for water, right? Don't really push it with air, right? Maybe sometimes just to get a rough idea, fine. But incompressible flow. Inviscid flow, meaning that no viscosity. That's an assumption we're still sticking to from the beginning of this class, right? So here we said there is no viscosity. There's no stickiness to any of the fluids we're dealing with, right? They just flow very freely. Okay, it's not like syrup. You just pour and it goes, right? So without viscosity, there's no stickiness to the fluid. That's an assumption of the Bernoulli's equation. Okay, so then you're like, well, blood has viscosity. Yeah, that's right? So if you're trying to apply it for blood flow, you got to be really, really careful, and most likely you'd use something a little bit more sophisticated than Bernoulli's equation to actually properly model it. The flow should be laminar. Okay, notice what I'm doing with these streamlines, right? So I'm assuming that it's very smooth. I'm not assuming it's tumbling and turning all over the place, right? So if you have turbulent flow, don't apply Bernoulli's equation, right? Okay, and the other one that's maybe less strict, but it certainly has to be said, is you apply this along a certain streamline. Okay, so in the case of applying Bernoulli's equation, I said, well, there's also another streamline like this. I'll try to draw it in a faintly, right? So there's another streamline like this, there's another streamline like this, right? There's many streamlines, right? So there's all these streamlines that happen. So if you start off at this streamline and you measure the height here, and then you go to a streamline over here that is not the same, and you measure this thing's y value over here, that won't work, right? So you have to stick to the same streamline. So if you pick a streamline and you measure its height, you better stick to that at the end and measure that thing's height, right? Not something else's height. So use one streamline to apply Bernoulli's equation, right? So please be careful. Don't misuse Bernoulli's equation. It doesn't apply to everything and anything that involves fluids, even though people use it for that. So be careful. All right, so given the caveats, let's list Bernoulli's equation, right? So again, it's relating properties at the beginning to the properties at the end, okay? 1 and 2. So I'm going to write the pressure at the first point plus 1/2 rho V1, velocity, not volume, squared, plus rho G Y1 is equal to pressure 2 plus 1/2 rho V2 squared plus rho G Y2. Okay, so this term, right, should kind of remind you of MGH. It's sort of like MGH, right? Because if you multiply this term, rho g, right, y is a height, right? So imagine that's your h. There's your g. Rho is a density, but if you took this and multiplied by volume, that's mgh, right? So it should kind of remind you about potential energy if you've seen it before, right? If not, no worries, we'll get to that. This one is like kinetic energy, right? 1/2 mv squared, right? So we'll get to energy later in the class, but this equation is really a statement of the conservation of energy. It's saying that energy at the beginning is equal to the energy at the end, that you can't create or destroy energy, okay? That's essentially what this is kind of getting at. More on that, you'll appreciate this a bit more once we talk about energy and work and things like that, right? But what is it doing for us? It's relating properties at the beginning to the properties at the end, right? So depending on what you're trying to solve for, maybe you don't know the velocity at the end of this pipe, but you know everything else. You know the pressure at the beginning, you know the pressure at the end, you know the velocity at the beginning, you know what the heights are. This will allow you to solve for the velocity at the end, okay? So it's a bit more complicated than the continuity equation, but all of this is built into this. Okay, so this is a more comprehensive equation so long as you're following the caveats, right? You're not applying it where it shouldn't be applied, then this is a very handy equation to use, right? So good for the fact that it relates a lot of things together, bad for the fact that it is very restricted, right? So it's you got to be really careful using it. Questions about this? We doing okay?
Yeah, so far.
Cool.
Question just popped up. When would you use this equation versus the other one? I'm assuming it's the continuity.
Oh, continuity? Yeah, so continuity equation, pretty good. if you don't really have any changes in height, right? All you have is a change in the size of your pipe, right? It's flat, it's going along the ground, it's not making any changes in height, right? That's pretty good. Also, it doesn't really require you to know anything about the pressures, right? It requires you to know the size and the flow, right? How fast is the flow? It doesn't really get to the pressure, right? So the Bernoulli's equation, a lot more sophisticated in the sense that it gives you a little bit more detail, but it also requires more information, right? So you need to know what the pressures are, something. You need to, if it's one equation, you can only have one unknown in here, right? And a lot of these things need to be determined, right? So you need to know the properties of the beginning and the end fairly well to use this, right? If you think about actually using this in practice, because that could be an unknown, that could be an unknown, right? Maybe that's an unknown, but hopefully you can measure that. That could be unknown, that could be unknown, right? So there's a lot of unknowns that's a possibility, which means that you can only have one unknown in one equation, right? So you need to know a lot about the flow you're dealing with, right? So you need to measure the pressures, let's say here and here, for instance, to determine the velocities. Right? If you knew the velocities, okay, fine. Then maybe, but still, you need to know. You can't know both the pressures by just knowing the velocities, right? That makes sense, hopefully. Okay, let's apply this carefully as much as we can to a scenario that doesn't violate these conditions too much. It still does, because we're gonna well, if we imagine a real scenario, it will, because so I'll tell more about this. So just kind of be aware of these caveats. Let's try to come up with an example where you can actually use Bernoulli's equation. Okay, and what we're gonna do is have a tank like this. And there's an opening on the side of the tank. We're going to fill this with a fluid. Okay. So now you might, let's pause. What can we fill this with, right, in reality? Coming back here. Okay, if we use a liquid, this is fairly incompressible, so that's okay. We can set up a scenario where we have laminar flow, right? Water can flow in a laminar sense. We can certainly follow a streamline, right? We can add dye, right, to see the streamlines, visualize them, and apply Bernoulli's equation. This is really the hardest thing to kind of get away from, right? It's really, really hard to find fluids that have zero viscosity, right? So if you talk about water, it has a viscosity, right? If you talk about syrup, it has a viscosity. Oil, it has a viscosity, right? So perfectly zero viscosity, that's hard to find in practice. So let's imagine a scenario where you have a fluid that doesn't have any viscosity, or the viscosity is extremely small, okay? And let's say that's what we are filling this with. And then that way we can still apply Bernoulli's equation. So we want to figure out what is the velocity, right? So if you fill this with fluid and you leave this open at the end, of course this will flow out, right? So there will be a flow out this way. And we want to know how fast it's going to come out, how fast it's going to flow out, okay? So what we can do is treat one of these points. This point could be 1 or 2. It doesn't really matter. Right? Your end doesn't have to be 2. Your end can be 1, right? It doesn't really matter. They're just reference points. So I'm going to treat this as velocity 1. Okay? This is our condition, our case 1. We need a second, right? So here we need to figure out beginning and end point. So that's the end point. That's where it flows out. Where's the beginning? Well, what we have to do is track this flow all the way along a streamline, right? So I'm going to draw this like this. Imagine if you could see the fluid actually moving. And if you add a little bit of dye, maybe you can actually see this motion. So if you see the fluid, it's this motion, right? It comes out this way. This fluid, right, let's imagine doesn't end up here, right? Let's say this is what we're going to track. We're going to say that the fluid that was here is going to flow very smoothly down here and end up out here, right? That's what we're going to consider. And that's our streamline, right? So we want to apply it along a streamline. We're applying it along a streamline. And then at this point is going to be our point 2. Okay? So let's write Bernoulli's equation completely, right? So we'll say P1, pressure 1, plus 1/2 density, velocity 1 squared, plus density G Y1 is equal to pressure 2, 1/2 rho V2 squared plus rho G Y2. Right, so we're writing Bernoulli's equation. Now let's think about applying it. Okay, at the second point, which is up here, we can say that the fluid essentially is starting from rest. Right, that's not too bad of an assumption, right? So at the very, very surface, it's when it just starts off at rest and then gets faster and faster and faster and then comes out, right? So we can say that at this point, we'll get rid of the velocity, right? Just saying it approximately starts at 0. Okay. Now, we do need a pressure at this location, right? So maybe at this location, there's some gas in here, right? That gives the fluid just about a little bit of pressure, right? Just because there's some pressure at that point. So then we can say, okay, we need to kind of calculate the height. So this is y2, right? That's the height, let's say, from the bottom of the container. And then at this point, the height is y1, right? From this, so we want to get to just that level, right? y1. And of course, we have a pressure. After it comes out the nozzle here, there'll be a pressure 1. Right, so 2 pressures that we can potentially measure, right? Now, what do we want to solve for? We want to solve for this, right? The velocity as it comes out here. And you can do that. If you solve for it, you'll get the velocity 1 is equal to the square root of 2 divided by rho times P2 minus P1 plus rho G Y2 minus Y1. Okay, so I'll let you do the algebra. You take this equation, solve for V1. This is what you should get. Okay, so the expression itself is not that important, right? So different scenarios will give you different results, but it's interesting to stop and think about why is this velocity happening in the first place, right? Because these terms will tell you what's causing there to be velocity 1 in the first place, right? So look at the pressures, right? So if you pressurize the top of your container, P2 is greater than P1, right? I mean, let's say that's the atmospheric pressure as it comes out, then that's part of the reason that's shoving the liquid out the bottom, right? Just because there's a pressure. If P1 and P2 are the same, right? Maybe you poke a hole in here and set it as atmospheric pressure, then those two will be the same and they'll go away. This will go away, right? And that won't contribute to the velocity then, right? If the two pressures are the same, it won't push the liquid out. Then you can see what the second term is doing. The second term is like the gravity term, right? This is saying that why this has a velocity is because this material starts off with some something to begin with. That's potential energy. We'll see next time and carrying on in the next part of the class when we talk about energy. So this material right here has some potential energy, has some ability, right, to do something, and that's what's causing this to have velocity at the end, right? So there are two effects happening. One is the pressure that's pushing the material out, right? So if you know from, right, kind of experience that if you have high pressure and low pressure, things will flow from high to low pressure, right? So that's one thing. The other thing is a gravity term, right? And if you can imagine a scenario where you got rid of the gravity term, where the two different points are the same height, then the gravity term will not contribute to the velocity. You'd have to rely on the pressure term, right? So in this case, this container, there are two effects that's causing the velocity in the first place, right? So kind of an example where we're trying to be careful with Bernoulli's equation and apply it as carefully as we can. Bernoulli's equation in practice is very limited, right? And if you try to think about everyday examples where Bernoulli's equation is properly accurate, there's not very many, right? So it's kind of a highly idealized equation. However, it is useful in the sense that you kind of see how things work, right? You see the effects of the height changing, you see the effects of the pressures changing, right? So you kind of get a rough idea of how flow behaves. So long as you have these restrictions, you can use it, but just be really, really careful when you're using Bernoulli's equation that you're not just applying it to random scenarios that don't meet the caveats. Okay, so let's talk about midterm 2 towards the end of the class in a second. I'm going to briefly talk about viscosity. Right, I've been putting aside viscosity the whole time, right? So you're saying we're not dealing with viscosity. Viscosity makes everything very complicated. So I highly recommend, if you're interested in fluids, take a class entirely on fluids, right? It's very useful, particularly if you're going in that direction in your career, in grad school, what have you. It's to your benefit to take an entire class, properly go through fluid dynamics. It does take an entire class to just do that, right? But I'm going to give you a little flavor of what viscosity is, right? And that way you have an idea, hey, what the heck is it? So viscosity, like I said, the kind of descriptive way of thinking about it is say it's the stickiness of how fluids flow, right? Good example to compare to is syrup versus water, right? And where you can kind of see this effect is if you go to your swimming pool, right, or go to the UT swimming pool, put some object on top of the water, right? So here's the water, and here's the bottom of the swimming pool. Okay, so here's the water. And let's say you put some object on top of it, right? Kind of like a floaty or something, right? And you put this right at the top of the water, let it float, okay? And then if you drag this across, put some force, drag this across, what would happen to the water that's below it, right? Try to imagine what would happen, right? Because of viscosity, this water is going to stick to this board right at the contact point, right? Because of stickiness, right, of the fluid, this board's not just going to glide through the top of the water. When you pull this board across, the very surface of the water is going to kind of get dragged along with the board, okay? So if you imagine the velocity of the material just near the board is going to look something like this. It's going to have a fairly high velocity, because the harder you pull, all that material will try to go with the board. But as you get further and further away from the board, right, down here, the water down here really doesn't care about the fact that the board was pulling the top water, right? At the very bottom, maybe it's affected by a very tiny bit, right? There's a certain velocity. So you get this kind of profile that looks like this in terms of the velocities. Okay? The closer you are to the board, you're going to get the water to flow in the same direction you're applying the force. Okay? But the further you get away from the board, it's not really being affected at all by this. Okay? So one way to measure or just kind of state what viscosity is, Greek symbol eta, ETA, is the force that you apply times the distance, okay, this distance right here, let's say your depth of your swimming pool, that distance, divided by velocity times the area. So the area we're talking about is this area, okay, and viscosity is a measure of kind of how this works, right? So that's one way to think about viscosity. So just to get you kind of a rough idea of, just so you're aware of what viscosity is, it's kind of stickiness, right? And the only reason why this is happening is because the water is sticking to the board, right? If you turn viscosity off, right, this was not, that didn't have any viscosity at all. If you drag the board like this water will not care, right? It wouldn't get dragged along like this, right? So if you turn viscosity off, the water will not care. Maybe it'll be disturbed a little bit at the very top just because you kind of moved it, but it will not have this sort of profile. This profile, right, of dragging the water across happens because of viscosity. Does that make sense? Just give you a rough idea what it is, right? And when you add this to fluid flow, it makes everything very, very complicated. Okay, so you have to go through a much more rigorous analysis to analyze flow that has viscosity in it, right? And why is it important? Well, airplanes don't work without viscosity, right? So it's not something that's optional that we kind of throw aside. It is a fundamental idea, right? But unfortunately, that fundamental idea is also very complicated to deal with. So for the kind of general physics, introphysics, it's, I think, just enough, okay, to just have a rough idea what this is. But highly recommend, take another class entirely on fluids. You'll get more into what viscosity is. Okay, questions about that? And we can certainly talk about this and then talk about midterm material, anything that's confusing that we can go over too.
We have a question about if viscosity will be on the final.
No, so we're not going to talk about viscosity at all, really, right? So I just want to show this so that you are aware of it. We will apply Bernoulli's equation carefully, right? So there will be scenarios like this where we're being very, very careful about how we're applying Bernoulli's equation. Yeah, so when it comes to fluid dynamics, it's kind of a tricky subject. It's very important. I love it. It's such an important topic. However, you just have to be really careful not to muck it up, right? So fluid statics is much more kind of straightforward, right? So if you talk about what is the pressure with depth if the fluid is not moving, that's fairly straightforward, right? It's an F equals ma situation. Buoyancy, right, is a very kind of straightforward idea, I think. But when things are moving, it becomes a lot more complicated. Great, so ask away questions about midterm materials, so homework 3, homework 4, right? Those are what we're going to cover for our midterm 2. If there's a question in the homework that you're like, okay, I'm not really seeing how to do this, this is confusing, that's a good place to ask. Lecture material that's so far, up to static equilibrium, right? So when you're talking about summing the forces, setting that equal to 0, summing the torque, setting that equal to 0. Ask about that. If you have questions about friction or dynamics problems, right? Dynamics meaning there is acceleration in F equals ma. How to set that up, let me know.
We have a question about, from homework 3. I don't know if you'd want to pull it up on Quest or just take a look. It's a block on a ramp, and we're looking for coefficient of kinetic friction
Let's take a quick look here. Okay, so homework 3, the block on a ramp, and the question is solve for...
Coefficient of kinetic friction and the frictional force.
Right, yeah, so let's see, cons... So for this question, did you do the first part? It sounds like you did, right? So the acceleration of the block you were able to find, right? So let's think about how to set up questions like that. Okay, so let me pull it up that way. And what number again? 7. Okay, 7. All right, so yeah, that's a good one. Let's go. Can we show the computer real fast? Okay, there we go. So I think this is the question you're asking about. There's a block. So starts off from rest at the top. There's an incline, right? Slides a certain amount down, and it says, what is the acceleration of the block, right? How did you do the first part? How would you do the first part? And everybody else can answer too, right? So how did you all do, because homework 3 was a while back, right? So you all did this. How did you do the first part? How do you get acceleration?
We have used the distance, time, and final velocity to find acceleration.
Right, so you can use kinematics, right? So since you have your tools, you don't have to ignore kinematics. You can use that. All right, so this is 30 degrees. It's probably different for everybody, but I'll put in what I have for what I'm seeing here. So 3.4 kilograms, and then the certain distance that it travels, right? Meters. Okay. And there's friction. They give you the distance and time. Using kinematics, what's a good equation to use, right? We can think about our velocities, right? Because it starts off from rest. And, well, we don't have a final velocity, so that's not going to work. What kinematic equation should we use here to get acceleration? So yeah, so we can say x is equal to x naught plus v naught times time plus 1/2 at squared. Okay. Remember, this, yes, is generally the kinematic equation, but here, when we say x, what do we mean? We mean this, right? Going down this way, right? So we can apply it to y, right? So we can apply it to different directions. So the acceleration is that way, right? This block moves because there's an acceleration that way. So the directions are consistent, right? It moves that way. That's the direction we're talking about. So effectively, what you're saying is something like this, right? You're saying that the coordinate system that you're using is x, y, kind of like that, right? Where positive x is down, right? That's kind of what you're saying. You don't need to say that, but like if it helps, that's essentially what you're doing here, right? So the initial position you can get rid of and say I'm starting from the 0 point. Then they give you this, right? So this number is given. For me, it's 2.17 meters. Starts off at rest, so get rid of that. The acceleration is what we're trying to solve for. We don't know that. And then the time they give you, right? So the time we have, we should be able to find acceleration, right? That way. So that's part one. Part two, they're saying what is the coefficient of kinetic friction between the block and the incline, right? So now we're dealing with forces. We can't really do kinematics, right? We could get away with doing kinematics as long as we're trying to describe motion, right? If they're asking for an acceleration, that's a description of how things move. And so you could do that, right? That's okay. But now we need to draw a free body diagram. We need to deal with this using F equals ma, right? So here's our free body diagram. You have to put all your forces there. You know about the normal force. You know about the weight. Okay, what else should be on this thing? Normal force, weight, what else should be on the free body diagram? That it? Friction, right? And we have to determine the direction of friction. This is going to slide down this way. So as it slides down this way, what does friction do? Kinetic friction opposes that motion, right? So we know kinetic friction is that way, right? So our coefficient of friction, that's kind of where we're going to get it from, right? Because that's where it is, right? Because friction, let's write it to the side. Right, so kinetic friction is equal to the kinetic coefficient of friction times the normal force, right? That's the one that is an equation, right? Static friction is the one that's an inequality. So that's an equation we can use. So we're trying to solve for this, right? So it's going to come from here. We just have to do F equals ma, right? Now, to this, right, yes, we use this coordinate system for this part of the problem, but we don't have to stick to it. When we're doing the second part of the problem, you can use a different coordinate system, right? So the one I kind of recommend using is this one, just to keep it simple, is to write x and y this way, right? And then you sum forces, right? And then the only vector you have to break down is the weight vector. That's your right triangle for the weight vector. And you do F equals ma, right? So sum the forces in the x direction. Well, that's the positive force of friction, not the normal force. Weight, well, the weight is made out of two components. That's one, that's the other one. So the x one is negative, right? So we have negative weight. This angle, right, as we've talked about, is 30 degrees, right? So it's equal to this angle. Do the perpendicular lines trick, right? So then we have what? Sine, right? Opposite. So we have sine of 30 degrees is equal to, here's the part to be careful about, there is an acceleration, right? And the acceleration is in the negative direction, right? It's in that direction because we said positive was this way. So negative, mass of the block, and the acceleration now you found in the first part, right? You can use that information, right? So that's one of the equations. The other equations, sum the forces in the y, positive normal force. This part of the weight is negative, so you get minus weight cosine of 30 degrees. That part is equal to 0. It's not accelerating this way in the y direction, right? So use this equation to solve for the normal force. You get the normal force using this equation. Once you know the normal force, you can take it back up here because the force of friction requires the normal force. Once you know that, this equation you can solve, right? This one right here, you can solve for mu k, the coefficient of friction. Right? Does that make sense? Kind of that's the kind of the order of operations here, right? Hopefully that answered the question, right? So bring your questions, right? So today's Thursday, we have class tomorrow, we have class on Monday, all leading up to the midterm on Tuesday. We'll do at the end of every class, if you have questions like this, we're happy to answer towards the end of the class. Come to drop-in hours. all right, today, tomorrow, on Monday, and ask us questions. That's a good place to work out any kind of point of confusion. So we'll stop here. We're done with fluids. Looking real quickly at the syllabus, what's coming up ahead. Can we switch over to the computer? So coming up ahead, we are done with fluids. We're moving to energy, right? So Friday and Monday, we're going to talk about energy. After the midterm, we're going to talk a bit about thermodynamics, and finishing off the class, we're going to talk about simple harmonic motion, right? So we're almost there. Midterm 2, let's get ready for that. So see you tomorrow.